All right, next we'll look at Venus, often affectionately called our sister planet, although some people have also called it our evil twin. And so we'll examine why that's true. But Venus, in terms of the inner planets, is most similar to the Earth in size and composition. Its radius is 0.91 times the radius of the Earth. So that means that it's almost as big as the Earth. Now in the inner planets, the Earth is the biggest, then Venus, then Mars, then Mercury. So Venus then most similar in size to the Earth. Its distance from the Sun is about 0.7 AU. Okay, so it's 70% as far away as the Earth is from the Sun, or 30% closer in. And so because of that, and because of the fact that light from the Sun follows an inverse square law, Venus actually gets about twice as much sunlight as the Earth does. And so just a little distance, a little bit of a difference in distance from the Sun can give rise to a big difference in the intensity of the light. And so that kind of catches up with Venus because of the fact that Venus has a very thick atmosphere that holds in heat. And then there's a lot more heat coming in from the Sun because it's getting twice the intensity of sunlight that the Earth does. So its atmosphere is mostly carbon dioxide. It's very thick. And what is CO2? Well, it's the gas that plants absorb from the Sun to create photosynthesis. It's also the fizz that you find in soda drinks, and it's what we give off a lot of when we breathe. We take in oxygen, we put out carbon dioxide. Then plants take in carbon dioxide and put out oxygen. And so it's a nice give and take between plants and animals on the Earth. But on Venus, it's extremely thick. And this comes from volcanoes, mostly. When we have volcanic eruptions on the Earth, too, we get a lot of carbon dioxide that's released. But we think that, for the most part, the carbon dioxide comes from volcanic eruptions on Venus. And this thick atmosphere is 100 times the atmospheric pressure of the Earth. And so on Earth, we have atmospheric pressure of 14.7 pounds per square inch. But on Venus, it's more like 1,400 pounds per square inch. And so when you're walking around on Venus, it's like the pressure, which is coming in from all directions, is like kind of carrying a car around with you, right? Smashing you down from all directions. And so this is equivalent to being 3,000 feet beneath the surface of Earth's oceans in pressure. And so this thick, heavy atmosphere on Venus holds in heat. And so because of that atmosphere holding in heat, we call this, by the way, the greenhouse effect. Which we'll look at in more detail in a few minutes. But the atmosphere holds in this heat, and because of that, it has even hotter temperatures than Mercury does. Remember, Mercury was only 0.4 astronomical units away, or something like 40% closer in, at least, than Venus. But Mercury can't hold on to its heat because it doesn't have an atmosphere. So the big difference with Venus is this thick atmosphere holds in heat, and so the temperatures range from something like 600 degrees Fahrenheit to 900 degrees Fahrenheit. So this is the cool, chilly nighttime side of Venus, 600 degrees Fahrenheit, which a lot of metals and rocks melt at that temperature. This is hot enough to melt lead. Okay, so when we get up to 900. So in terms of things that we can remember for Venus, then it's got the highest temperature in the solar system for the atmosphere. Now, not necessarily interior temperature, like in the core. We're not talking about that. We're talking about the temperature of the atmosphere. Yet, evidence seems to indicate that Venus once had Earth-like temperatures. And so we need to try to understand this a little better, because a lot of times people ask me, what good is astronomy? What practical benefit do you get here on the Earth from learning about space and planets and stars? And so usually what I tell them is that, and this is a great example of where you can use it to help the Earth, is you can look at these planets as being basically just little experiments that you're running, where you turn the knobs on the control board a little bit differently. And so for Venus, you put it in 30% closer to the sun, and see what happens. And then maybe you can learn something. For example, we see that Venus, we think, had Earth-like temperatures, but that something went really wrong. And so we can maybe learn from that. And because the Earth is a little extra time being farther out, we might be able to prevent the same thing from happening to the Earth. And so those are the sorts of things that you can do that are practical and that could be very significant to us being able to keep the Earth habitable for a lot longer in the future. But the basic idea here is that the sun is getting hotter. And we'll talk more about this later, but the fact is it's getting hotter about 10% every billion years. And so the evidence then indicates that Venus once had Earth-like temperatures and maybe even water oceans. So it really was more like the sister planet to the Earth in the past. Because the sun was cooler. So now we see that Venus is getting twice the intensity of sunlight that the Earth does, and that was also true in the past. But in the past, the Earth was much cooler. Now, the sun has gotten hotter, and so Venus has gotten overwhelmed with light from the sun. And so what I'd like to do is show how the Earth handles this. And we think that this is also the same kind of a thermostat mechanism that Venus had at one time. So what do I mean by this? I mean, well, if the sun's getting hotter, how does the Earth manage that and still maintain a habitable surface temperature with temperatures within the range that water can remain liquid? Because if water doesn't stay liquid, then we don't have the raw materials for life, at least the kind of life that we're familiar with. Okay, and so on the Earth, here are the oceans, and then we have sunlight coming in from the sun. So that causes evaporation. Then that evaporation turns into clouds. The clouds move over the land. Sometimes there's orographic lift, which forces the clouds to higher elevations, and then that cools the clouds off. We get rain. Then the rain goes into big pools of water, streams, and eventually flows back out toward the ocean. But in these pools and streams, we have erosion of calcium minerals in particular, lots of other minerals too, but the one that I'm interested in for this thermostat mechanism is calcium. Into this water environment. And so then what happens is that the calcium combines with carbon dioxide and water, and the result of all of this then, and the carbon dioxide is coming from the atmosphere. Okay, so here's the CO2 in the atmosphere. And so the CO2 then is pulled out of the atmosphere, combined with calcium and water to produce calcium carbonate, which is limestone or rock. And then some other gases are given off. This isn't a balanced chemical reaction, but this is the basic idea, is that you take calcium from the erosion of the minerals that are then suspended in the water, and you combine that with carbon dioxide, and you can make rock. So what is this? This is a mechanism for pulling CO2 out of the atmosphere. Why is that important? Well, CO2 is a greenhouse gas. And so let's just imagine that these are a bunch of CO2 molecules in the atmosphere. And then here's the surface. And so what will happen then is light comes in from the sun. Some of it makes it through, some of it bounces off. Okay. Now, if we take a look at the data projector up above, we see that Venus does have a bright side to it and is quite visible from the Earth, even though the darker side is the side that's pointing away from the sun. So you can actually see Venus in phases, and we'll talk a little more about this later. But the fact is, a lot of the light that comes from the sun does reflect off. and that light can go to us so that we can see Venus. And this is true for other planets as well. You get a lot of reflected light. But then some of the light makes it through to the surface. Okay? And so the light that makes it through to the surface then turns into heat. Okay, so the light turns to heat at the surface. That heat is called infrared. And the infrared gets trapped. And so the infrared then gets bottled up. Okay? It is absorbed by the CO2 and then re-radiated back. And so the carbon dioxide molecules don't let it out. And so then the heat builds up. And so this is why on Venus we've been able to get such horrendous temperatures between 600 and 900 degrees Fahrenheit, because this heat just builds up. The same sort of thing happens in your car. Say you don't put a sun reflector on your window, on your dash, and then you go out to the beach on a nice hot day, and then you come back and you get in your car and you still have your bathing suit on, your legs start to burn, okay, and you scream, and then you grab the steering wheel, scream again, and so you frantically are trying to roll down the window to let the heat out. Okay, so that in your car, it's the light coming through turning to heat when it hits the seat, and then the heat can't get back out through the glass. Okay, so the glass is like the carbon dioxide here. So when you roll down the window, that's what we're doing to this thermostat mechanism, is we're rolling down the window. We're allowing more heat to escape, but we do that by pulling carbon dioxide out of the atmosphere. So if we have a lot less of these carbon dioxide molecules, then the light that hits the surface, some of it will still turn into heat which is trapped, but a lot of the heat can escape. Okay, so it's just like rolling down the window. And so this can compensate then for solar heating, because the sun is getting hotter. So what do you need to do to compensate for that? You need to remove more carbon dioxide. And so that's what our thermostat mechanism over here does, is it removes carbon dioxide from the atmosphere, and that allows more heat to escape from an ever increasingly hot sun. Okay, and so as the sun gets hotter then, you get more evaporation, right? More evaporation means more clouds, more rain, and more erosion of calcium minerals, more absorption of CO2. And there are other mechanisms for this too, what's called acid rain. When you get water dropping out of the atmosphere, that can directly interact with carbon dioxide to produce carbonic acid. And that carbonic acid can help in the process, this acid rain can help in the process of eroding the calcium minerals, and then eventually these minerals are swept into the sea and can form sediment layers of limestone, and also in coral reefs you get limestone being produced in a similar process, absorption of CO2 and the formation of the limestone structures in coral reefs. Chalk is another example of the formation of calcium carbonate from calcium, CO2, and water. Okay, and so this is working just fine on the Earth then to cool the Earth's temperature down as the sun gets hotter. But what if the Earth were to freeze? So if it gets too cold, this is fine then if things are getting too hot. But what if it gets too cold? Does that ever happen? Yes. 550 million years ago we had what's called snowball Earth, where all of the oceans, we think, were all frozen over, and almost all the way to the bottom, possibly, in some places. And so the idea there then is that if things get too cold, that's the other aspect of the thermostat. The thermostat heats things up, cools things off if they get too hot. But if they get too cold, it heats things back up again. And so thermostat has to be able to do that too. Otherwise, the Earth, when it gets to a point like that, could turn into a big ice ball. And then the ice reflects so much of the light that none of it's absorbed, and so it just keeps getting colder. So what's going to stop that from happening? That could destroy life too. Well, too cold means that the ice surfaces prevent evaporation. Of the oceans. So that was the first step in our thermostat mechanism, is that we had evaporation and then that formed clouds. Okay, but when you get an ice surface, that prevents the evaporation of the oceans. But you still have CO2 being produced by volcanic eruptions. As long as the Earth has a hot interior, you can still have CO2 produced by volcanic eruptions. So given that this is the case then the CO2 can build up and it's not being pulled out. And so it can block the release of heat. And as the CO2 builds up, that causes warming by greenhouse effect. And then the ice melts. Okay, and so then we have liquid water oceans again. But what can happen in a process like this is that it overshoots. So you end up with the levels of CO2 versus time. Okay, first the CO2 levels are too high, and so they're brought down by the thermostat mechanism. Okay, but then we get to this minimum point, so at this point where the CO2 levels are too low, things freeze, okay? And so that means the CO2 levels can get back up, and so they get back to a point that would be just right for maintaining the temperature, but then they continue to grow, and then the CO2 levels get too high. Okay, and so with the CO2 levels too high, then it heats up again. Heats up too much. And here it's cooled off too much. And so then it's the CO2 levels are too high, then the thermostat mechanism goes back into full gear because it's way too warm, so that causes a lot more evaporation. That pulls a lot of CO2 out of the atmosphere, and then it drops down, but it still goes too low, and so it freezes. So you get super hot, super cold, super hot, super cold, but slowly it tamps out. So this is what we think happened over something like, maybe this here was 700 million years ago. And then down here, this is maybe 550 million years ago. And finally, the overproduction and then the too much conversion of CO2 into rock, and then too much CO2, too much conversion into rock, finally smooths out to a stable level of CO2, which is associated then with a stable temperature. And so this is the two different aspects of the thermostat mechanism pulling us out of the snowball Earth scenario. And so we think that this sort of thing was happening on Venus too for a while. But then what happened to Venus? So Venus had the same mechanism working to maintain its surface temperature as the sun gets hotter. But eventually on Venus, all the water evaporated. It got too hot because it's closer to the sun than the Earth is. It's getting twice as much solar radiation. So it means the same thing is in store for the Earth in the future as what has already happened to Venus. And this is how we can learn so much from Venus and hopefully prevent this from happening to the Earth. But once all the water evaporated, then the thermostat mechanism is broken. That's how it does its thermostat mechanism, is with liquid water. And so that means the CO2 levels can continue to increase. And then the more they increase, the hotter things get. Water, when it all evaporates, that's also greenhouse gas. Water can help block the flow of heat. It's maybe only 25% as effective as CO2, but it still plays a role. Also methane gas. We have a lot of stored methane ice from earlier epochs, and so once that all evaporates, that will also put more greenhouse gases into our atmosphere. So eventually then, we think that the Earth is going to follow in Venus's footsteps. Okay? And so here then we get what we call a runaway greenhouse effect on Venus. And this is the reason why the temperatures are so great on the surface of Venus. Whereas on the Earth, we still have water. And so that means our thermostat mechanism can work until finally we'll reach a point where there's no more CO2 in the atmosphere. And at that point, all the plants will die. And that'll also be the point where that kind of regulatory mechanism won't work anymore, and that's when we expect that our oceans will evaporate.